So much, and welcome back to the second half of this morning's session. Kicking us off, we've got Dave Heslop, and he's going to be talking about quantifying the role of iron minerals and climate change. What do you think?
Right, thanks, Ron. Yeah, so when I was putting this presentation together, I realized that I had a lot of questions and not many answers. So you're going to have to humor me a little bit, I'm afraid. But yeah, quantifying the role of iron minerals in climate change. And as an opening example, I wanted to show you this image of a dust storm in 2020. This is known as the Godzilla dust storm because it was so large. And you can see that in North Africa, we've got these kind of yellowy, orangey dust that is rich in hematite and goethite. I say rich, it's actually only a few percent, but it's so highly pigmenting that you get these orange and reddy colors. And the material is being deflated and then blown over the Atlantic in these large quantities. And this is kind of one of the processes that I'm going to be talking about. So bringing it to the iron cycle, hematite and goethite are ubiquitous weathering products in the Earth's regolith. And again, when we look at these kind of satellite images, look at somewhere like North Africa, we can see these yellows and orange colors. I'm going to be talking about Australia as well. You can see these slightly darker oranges colors due to the hematite and the goethite that's in the material. And the wind picks up the dust, transports it through the atmosphere in this generally referred to term as mineral-rich dust. Now, this has a number of influences on climate during transport. You can see you're going to get scattering of solar radiation, deposition on land. When you get this dark mineral dust deposited, for example, on snow and ice, it leads to warming and premature melting. And something that's already been talked about this morning by Ali, deposition in the oceans. We've got mineral-rich dust, hematite and goethite being deflated and blown into the ocean. So I'm going to be mainly talking about transport and deposition in the oceans, but deposition on land is important as well. So here we can see these iron minerals are going to be directly influencing the climate. So in environmental magnetism and rock magnetism, we're used to thinking about hematite and goethite as proxies for dust and climate. So this is a really nice example from a study by Lawrence Sonia et al. 2003, and they took a marine sediment core from the Mediterranean and using, for example, HIRM and AFD magnetized IRM, they used these as proxies for hematite and goethite abundance, and then showed that during dry periods and arid periods, you had greater concentrations of hematite and goethite because more mineral-rich dust is being blown into the Mediterranean. And then during warmer periods, the monsoon in Africa moved further north. It actually vegetated that area around the Sahara, and dust transport became lower. Okay, so they were able to take the proxies of hematite and goethite and relate that to the climate state in terms of, was it an arid period, was it a wet period, and so on. And that's something that's quite familiar to us in terms of environmental magnetism. Now, in Australian context, we have very big continents, and there's a lot of desert and dust source areas that are rich in hematite and goethite. So this at the top right is a collection of samples that we have at the ANU from all over Australia. And you can see that we have bright red samples, bright yellow samples suggesting hematite, goethite, but also a whole range of things. We're going, dark colors as well. But generally, it's accepted that these dust source areas are rich, in inverted commas, in the hematite and goethite. Like I said, typically it's just a few percent, but they're strongly pigmenting. When this material is in the atmosphere, it can have two main effects with respect to solar radiation. The first one is an indirect radiative effect. And this is an example of a dust storm off Western Australia, where the dust in the atmosphere has actually caused this formation of a cloud system. And then that cloud system interacts with the solar radiation. So it's having a climatic effect, but it's an indirect one because it's the dust causing the cloud, and it's the cloud that's interacting. But we also have a direct radiative effect. So this is a huge dust storm that came through Sydney. You can see, again, the orange yellow color due to the hematite and goethite in the dust. And this is causing scattering of the incoming solar radiation. So that's referred to as direct radiative effect. And that's something that I'm going to be focusing on. So the way that this dust has a direct effect on Earth's energy budget depends on whether it's absorbing or reflecting solar radiation. So we have our dust source area out in the desert. We get erosion, the wind blows, moves this dust into the atmosphere. It has horrible health effects. But up here we have the incoming solar radiation, which may be reflected by the dust, or alternatively, it may be absorbed by the dust. And what that really depends on is the color of the dust. So if it's a light color, solar radiation is reflected and we get overall cooling. If it's darker colored dust, solar radiation is absorbed and we get atmospheric warming. We also get heat coming from the ground, which might be absorbed or reflected back to the ground. And then we've got these indirect effects that I talked about earlier. So, for example, cloud formation and also melting of snowpacks and ice when dust is deposited on them. But the key message here is that depending on the dust, we can either get absorption and warming, or we can get reflection and cooling. And this is a summary graphic from the most recent Intergovernmental Panel on Climate Change report, where they looked at the forcing effects of different processes with respect to climate. So what this boils down to is radiative forcing in watt/meters squared. So where we have a positive radiative forming, that's going to mean that we have a warming. And where we have a negative radiative forcing, that means we're going to have a cooling. So not surprising, something like carbon dioxide has a strong radiative forcing, and it's going to ultimately cause warming. What we have along the axis here is the level of scientific understanding associated with that process. So again, not too surprising, we have a high level of scientific understanding with respect to the effects of CO2. Now, by the time we get to mineral dust, here, you can see the level of understanding is very low. And it may be positive radiative forcing, it may be negative. We don't even know the sign of dust direct radiative effect in terms of will it warm or will it cool. So obviously that's a bit of a problem. And why don't we know the sign of the dust DRE? Well, again, that comes down really to the color of the sediment. So this graphic shows we've got two different source areas in the desert. We've got one associated with a light colored dust that's deflated into the atmosphere. It reflects the solar radiation and we get cooling. But then maybe in a slightly different area with a slightly different mineralogy, we've got this darker colored dust, goes up into the atmosphere and it absorbs the solar radiation and we get warming. So this satellite image on the top right is from northern Libya of a dust storm. And you can see even that within this relatively small local area, we've got two dust sources with quite dramatically different colors. We've got a light colored dust that's probably going to reflect solar radiation, and we've got a dark colored dust, probably rich in hematite, that's going to absorb solar radiation. So this then causes a real problem when it comes to things like climate models. And once we try to build dust activity into the climate model, what do we actually do in terms of reflectance? So the reason that we don't know the sign of the dust direct radiative effect that we saw in that IPCC summary graphic is because we don't know the composition of the dust. Okay. So this is an example of a NASA climate model where they have dust incorporated into the model, and you can see these kind of yellows and oranges here. This is showing the pattern of the dust being transported from North Africa, Southern Hemisphere. You can see there's a little bit from Australia, South Africa, South America, and so on, but it's really up here that the main activity is happening. But the colors in this representation are just for visualization. Once they're actually working in the model and trying to work out what color or what reflectance to give the dust, it's really poorly quantified. So like I said, the reason we don't even know the sign is because we don't know the dust composition. So in the climate modeling world, people are kind of worried about this. The physics of the dust DRE is well understood. But what limits its application in climate models is our knowledge of dust composition. So the climate modelers go through and they think about these things and they run models with different scenarios. And this paper by Lee et al. In 2021, we're going to run a little quiz here. We want a show of hands. People on Zoom, I'm sorry, but you won't be able to participate. What percentage of the uncertainty in quantifying the global direct radiative effect of dust stems from uncertainty in dust hematite and goethite abundance? So who thinks it's 5%? Who thinks it's 33%? Okay, one hand at the back. 67%? 97%? 123%? Okay. It's actually 97%. So when we look at that IPCC report and that uncertainty bar, 97% of that uncertainty comes because we don't know the amount of hematite and goethite in the dust. So NASA's decided it needs to do something about this, and it's launched the EMIT mission, which has the rather tortured acronym of Earth Science Mineral Dust Source Investigation. Okay. And they launched, EMIT is a spectrophotometer. So you can see it mounted on the International Space Station down there in the little red circle. And the idea is that it takes the light reflected off the ground surface. It's picked up by the spectrophotometer on the ISS. And then they can analyze it. And when they go over the dust source areas, the inference is they're measuring the ground, the reflectance of the ground, but the inference or the assumption is that the dust will have the same composition as whatever's on the ground. So they can then quantify that. So you go from your spectral measurements. From that, they use an algorithm to infer what the mineralogy of the ground is. Once you know that, you then plug that into your climate model until ultimately you're making predictions about the climate future and hopefully incorporating realistic information about dust. So EMIT, it's a year-long mission, but it's probably going to get an extension. It measures each grid cell or pixel that it's measuring is 60 meters by 60 meters. And it's fair data, so it's open access. You can download it and you can work with it. And all the processing algorithms are open source as well. So you can download the processing that's all in Python and you can process the data yourself. What they're aiming for is coverage of modern dust source areas and also potential future dust source areas, because as the Earth warms, it's going to become more arid. Those source areas are going to expand. So we need to know what the hematite and goethite is in those source areas as well. So the little blue squares are the measurements to date. And I think the mission's got a few more months to run, and they're going to try and fill in a little bit of this map a bit more. But like I said, they're focusing on the main dust source areas. So what EMIT is doing is measuring this reflectance between 400 and 2,500 nanometers in these 60 by 60 meter squares. So this is an example. This isn't actually EMIT data, but it's an example from an earlier mission where they basically take this image with lots of different wavelength channels and then look at the spectrum for each pixel. And they're looking at characteristic shapes in the spectra and comparing it to a reference spectra that they've got tens of thousands for. And ultimately, what they're trying to do is estimate 10 key minerals, which they estimate the abundance of using this so-called tetracorder algorithm. So of those 10 key minerals, there's lots of them, but hematite and goethite are the two main ones that they're interested in. And then ultimately, you can produce a map like the one on the right, where in this case, each pixel is just shown in terms of the most abundant mineral. But if you actually look at the data, once it's been processed for each pixel, you have the abundance of all 10 minerals recorded in there. Actually, they do a lot more than 10 minerals. They're just not including that in their data products that they're outputting. So you can still go in there, and if you're interested in a different mineral, you can still process and get an estimate for that mineral abundance. Now, coming to the kind of rock magnetic quantification of hematite and goethite, we've got a large number of samples from all over Australia, which you can see with the different colored dots on the map there. The dots just represent different biogeographical zones. So that's all they are. And we've been doing simple experiments such as IRM acquisition. So at the top left, you can see IRM acquisition for 3 samples from different deserts in Australia. The color of the lines represents the color of the sample. And we've got our magic 300 millitesla cutoff line that we use for HIRM and S ratios and so on. And you can see they've got really quite different behaviors, particularly the one from Pinnacles Desert, which is goethite rich. You can see it requires very little IRM compared to the other samples. But we've clearly got a high coercivity component. Another experiment that we did was to take the material and actually sieve it. So it's thought that in terms of dust, the material that's picked up and transported in the atmosphere is less than 20 microns. So we took the bulk sediment, sieved it, got out that fine fraction that's potentially deflatable, and measured the IRM as well. And when you look at the two IRM curves, you can see that in this high field region, they are actually different. Now, one of the things that EMIT has to assume is that the dust is going to have the same composition as the ground surface. But what we're able to show quite clearly with these simple IRM experiments is that the dust and the land surface are different. So this may be an issue for EMIT, and it's the kind of thing that we can test quite easily using environmental magnetism. But of course, hematite and goethite are challenging to quantify. So what do things like HIRM and S ratio actually tell us? And these are the kind of conversations we've been having for years, sorry, decades. And here's an example from Andrew's paper in 2020. This is a replot of actually data that Roy Thompson put together of sized hematites. And what you can see again with our magic 300 millitesla line is that when we're talking about large hematites, some of them are acquiring maybe 80% of their SIRM before 300 millitesla. Even when we're down at the, the fine stuff, sometimes it's 30, 40, 50% of the IRM is acquired before 300 millitesla. So that's going to have some influence on our estimates of HIRM, S ratio, and so on. Then on the right-hand side is a compilation that Andrew put together of synthetics and different natural hematites. This is now backfield measurements. And you can see they have dramatically different coercivity distribution. So again, if we're talking about, let's try and quantify hematite and goethite in dust, it's actually really difficult using just things like HIRM and S ratio. But of course, they are indicative and can help us try to solve the problem. So what can EMIT do for environmental magnetism? Well, if you're interested in potential source areas, you're now going to have these really high resolution mineral maps showing you, at least as far as their algorithms are concerned, how much hematite and how much goethite there are in these different places. If you're going to certain sampling areas, you could look at the EMIT maps in advance and give you an idea of mineralogy. If you're looking for certain type materials, so you want a really nice hematite-rich sample or a really nice goethite-rich sample, you could actually look at the EMIT data and try and work out where you might find that. So what it's doing is providing a complementary technique. It's free, but of course it's also limited. So there's a lot of assumptions that go on from making a measurement from the International Space Station and from that actually trying to infer the amount of hematite and goethite. But it's there and it's certainly complementary to what we're trying to do. In terms of what environmental magnetism can do for dust DRE estimates, of course, one of the key things is reflectance is more important than composition per se. It's the color of the material that's controlling DRE. And we know that, for example, hematites can have a huge range of different colors. So it isn't necessarily a priority to work out how much hematite I have, how much goethite, rather what types of hematite and goethite you may have and what their reflective properties are. Something I didn't touch on before that I think environmental magnetism can contribute to this that missions like EMIT can't is particle density. So when EMIT looks at a ground surface, if, for example, you have quartz particles covered in a hematite coating, EMIT just sees hematite. Using environmental magnetism, we may be able to infer whether this is a solid hematite particle or whether it's a quartz particle with a hematite coating. Now, the reason that's important is those two different particles would have dramatically different densities. And the density information is needed for the climate models because it controls how long the particle will actually reside in the atmosphere for. Obviously, if you've got a more dense particle, it's going to fall out the atmosphere quicker than a less dense particle. Okay, so that kind of information is needed for the climate models. This kind of information that EMIT can't provide. This is probably the most crucial one. Magnetism can provide paleo information. So whether we're looking at marine sediment cores, whatever, we can actually go through and reconstruct hematite and goethite through time. And this is where we maybe need to think in a little bit of a different way than when we're looking at the Mediterranean example and hematite and goethite being used as tracers, but rather hematite and goethite are active players in the climate system. They are actually controlling the climate as well as using them as tracers to try and define what the climate state was. So that's important when we've got paleo information available to us. Also, magnetism is going to tell us about sources and sinks, so we can go to our sediment cores and actually work out, where the material was being deposited. So that's going to give us information about source areas, pathways, and all of that's needed for the climate models as well to make sure that those representations of dust that they have are accurate. The dust is actually being transported in the right places and so on. So I think mineral magnetism and environmental magnetism have a big role to play in this. Now, what I want to do is just quickly move on for the last little bit of my talk and talk about the role of iron in marine productivity. This is something that Ali discussed this morning, and ecosystem function. So if you go onto Wikipedia and just ask it to tell you about the global iron cycle, this is the image that you'll get. And you can see that, for example, there is atmospheric dust coming into ocean iron, but also something, again, that Ali mentioned earlier, was you get glacial sediments, iceberg sediments, and so on. So there's iron going into the ocean from various different places. And again, we've covered this already, so I'm going to go through it quickly. But iron availability may limit biological carbon pump and CO2 drawdown. So we've got phytoplankton in the upper waters. When they bloom, they photosynthesize, draw down carbon dioxide. Phytoplankton die, sink to the bottom, and we lock away this carbon dioxide. So it's thought that as much as half of global carbon dioxide drawdown during glacial interglacial cycles was resulting from the fertilization of marine biological production in the Southern Ocean by iron-rich dust. So again, we're not just using iron-rich dust as a tracer, it's an active component of the climate system. And people have had the idea that we can actually use this as a geoengineering solution to reduce atmospheric carbon dioxide. So you get your ship full of iron, you dump it off the side, you let the phytoplankton bloom, and then they draw down the CO2. Now, experiments like this have actually been banned, except under exceptional circumstances, because what people would do is they'd take iron-rich soil that you can see they're pumping out this red soil here, and they'd go and dump it in the ocean, and then come back and monitor if there'd been a phytoplankton bloom or not. And slightly confusing results as well, that sometimes there was, sometimes there wasn't, but it's a complicated process. So I'm not sure that people necessarily got a good handle on whether this works or not. As we move on, we've got numerical models of biogeochemical cycles, and typically, I'm certainly no expert on this, but from what I've read, that in these models, iron tends to be considered equally. So it doesn't matter if we're talking about iron 2 or iron 3. A lot of the models, it's just considered to be iron. And there's this interesting paper by Schoenfeld in 2018, where they were reconstructing dust flux from marine sediment cores in the South Atlantic and South Pacific. They reconstructed dust flux. They also reconstructed total iron based on X-ray fluorescence measurements, and quantified the amount of iron 2 as well. So they come up with this ratio of iron to iron 2. And their conclusion from this was that iron 2+ is highly bioavailable. So that's actually the iron that is being used by the phytoplankton. Whereas iron 3 was less bioavailable and not being used by the phytoplankton. So suddenly, speciation is important. When we have physical weathering, that's going to mainly result in Fe2+, then we have highly bioavailable iron, and that may fertilize and cause phytoplankton blooms. Alternatively, when we have chemical weathering, and we're talking more about hematites and goethites and so on, that appears to be less bioavailable. So this is potentially an explanation of why these different fertilization experiments in the ocean, some worked and some didn't, because it very much depends on the type of iron that you're actually putting into the ocean. And this is now part of a project that I'm working on around Antarctica, where we're using magnetic properties to quantify iron-bearing minerals in terms of the inputs around Antarctica, and then trying to trace that in terms of phytoplankton blooms and so on. So we're considering glaciogenic sources transported via sea ice and meltwater events, aeolian fluxes, the dust that I've been talking about, but importantly also tephras. Again, they're probably going to be mostly Fe2+ versus the dust, which is mostly Fe3+. So again, whether the speciation is important or not is something that we're hoping to untangle. One of the key transport mechanisms appears to be icebergs, and they get this eroded material, they transport it out into the ocean, and then they melt, dump the iron, and it causes a phytoplankton bloom. And there's actually examples from satellite imagery where you can see these huge icebergs drifting off Antarctica, and behind them for hundreds of kilometers are phytoplankton blooms, just as a trail. So clearly they are delivering iron in a form that can be used by the phytoplankton. So this is ongoing work. Like I said, afraid a lot more questions than answers. So to conclude, and I'm going to conclude again with some questions, but first of all, hematite and goethite are clearly much more than just traces. They are key to the climate system. So in terms of mineral dust DRE, as we saw, we don't even know the sign of that effect because we don't know how much hematite and goethite is in the dust. But this direct radiative effect is being controlled by hematite and goethite. So EMIT is currently mapping these different potential source areas. And if you go to the EMIT website, like I said, you can download the data, you can interpret it, you can play with their algorithms and so on. So kind of maybe one of my questions here is, how does this link with environmental magnetism? Is this something that we can contribute to? Are hematite and goethite important in ocean fertilization, or is it actually Fe2+ that's crucial and the hematite and goethite isn't playing a particularly significant role? So again, another question is, how can we test this on a local and global scale within our community? Okay, and I'll stop there. Thank you.
There's a question on.
Yeah, I have a question from Stephanie Brackville.
Mm-hmm.
That you go ahead and ask.
There we go. Hey, good afternoon, everyone. Great presentation, Dave.
Thank you.
So I'm curious, Dave, if you or anyone in the room is aware of efforts to collect atmospheric dust samples, particularly away from continents, like stations on ocean islands, for example, in order to measure the particle size distribution and the mineralogy and the density. Echoing some of your comments, that's a huge debate in the Southern Ocean. And the models in use for the Southern Ocean use a very low particle density on the order of 2.5 grams per cc. The models cut off at 20 microns. And I'm just curious if there's anything different, right? There should be something different about the behavior of dense and larger iron oxides, even just lifting them up off the ground and how far they can travel.
Yeah, so I mean, you asked specifically about offshore, which I don't know of. In Australia, though, we have a huge, we have a network of filter stations. When I say it's huge, I don't mean in number of stations, I mean in terms of area covered, but that's Australia for you. And we got a number of these samples, and unfortunately, they were all too weakly magnetic for us to measure. There's just not enough material on the filters for us to be able to pick up a signal. So that thwarted us a little bit. I don't know if anybody's aware of efforts to do something similar offshore or not. Doesn't look like it.
Great, thank you. Something to propose for those of us who go out on ships, something to propose. Thank you.
I have a question about EMIT.
Mm-hmm.
Is it possible that it could be used to distinguish between surface stuff and the airborne things?
So potentially, they have hopes that they would be able to distinguish dust storms, for example. One of the limitations on that is, first of all, you have to catch it, not physically, but you have to be in the right place at the right time to see it. But what there also is a global network called AeroNet, which is actually using various spectrometers and so on to measure the stuff when it's in the air. So what they're doing now is going through a process where they're comparing their inferred deflated dust compositions to what they're seeing from AeroNet as well, and actually checking if there is any coincidence between them or not. And I think if they can show that they can do it, then they're going to move forward with that. But the main aim is to map the ground and then assume that that's the same as the dust. Yeah.
Getting back to your discussion of the modern climate system, you talked about reflectance of the particles, but we're talking about the balance of absorption versus reflectance. Seems to me the key parameter is it's not just reflectance, but it's the emissivity of the particle. So have you thought about that?
Not personally. No, so that's right. I mean, it's the way that it's being represented in terms of the models is hematite and goethite. But then a lot of assumptions are made in terms of, okay, what does hematite and goethite actually mean? So within the models, what they have parameterized is hematite has a certain grain size and so on, and certain properties, and that's all parameterized in the model. And it doesn't fully take into consideration the natural variability that there is in the particle properties. So for example, when in the current dust models, how they represent Australia, all the hematite is exactly the same in Australia.
What size?
Off the top of my head, I don't remember, but it's based on soil atlases where they've geochemically quantified the amount of hematite and goethite, and the whole of Australia, I think, is covered by 15 data points, and the rest is interpolation, which is then where the problem comes in, that it's the quality of these soil atlases that is lacking. So EMIT will allow them to update this. So when we talk about hematite and goethite abundance in the climate models, that then hides a lot of subsequent parameterizations that are made as to what the physical processes actually are. Yeah.
I would just encourage you to think, you know, if emissivity is the critical factor, you know, then that opens up the range of all the other compositions. That could be.
Yeah, yeah.
All right, I know there's several people got their hands up. We're gonna have one more question and then we'll continue. So if you don't mind sticking around, Dave.
Yeah, sure. Yeah.
11:45. Who wants the question?
Okay, sorry, that's quick. That was a really marvelous summary of what we don't know.
Yeah, like I said, lots of questions. It's very, very Rumsfeldian. Yeah.
Very supportive comment. It was really nice. I would even go back, for example, when you talk about, we don't know a lot about the dust chemistry and the dust mineralogy with respect to the iron oxides. I actually tried to track down the optical properties of the hematite and the goethite that are being put into these models.
All right.
So starting off with the lead paper, starting now with the lead paper and then going back to try to trace what he used. It was very, very unsatisfactory. We don't know about the optical properties of goethite to actually make these neat calculations. So I don't think we know
how to model for the iron oxides, the ferric oxides, because we don't know their optical properties.
Yep.
But the minerals they use to do this were not what nature provides for us, for example.
Yeah, absolutely. So you look at something like hematite, which can go from being black through to bright red. Yeah, and that, as far as I'm aware, is not incorporated in the model. You just have a standard hematite. Yeah.
That's true. Now, that gets us into EMIT, but I'll just mention that Bruce and Keith here at IRM have looked at Mossbauer spectroscopy and low temperature studies of a number of dust samples, including about 9 from Red Dawn, and found that the goethite nearly everywhere, globally, we've looked at it in a few places, is nano-sized. So the goethite is nano-sized, and its occurrences with other minerals is really key to understanding its contribution.
Yeah.
Same with hematite. A lot of microcrystalline hematite, which wasn't accommodated in these models.
Yeah.
So all of this leads to issues, as you point out, with EMIT. Not only that, but there are a lot of major dust sources like Etosha Pan in Namibia that actually these surfaces change over a period of months based on precipitation and water inflow. And that changes the mineralogy of these surfaces.
Yeah.
From different kinds of smectites to calcite dominant dust and things like that. So we've got to keep a close watch on EMIT. What is it going to tell us? And furthermore, there are dark particles in the dust that aren't accounted for by, for example, EMIT or almost any other climate modeling products. But these can be proxied by magnetite, because magnetite often occurs within dark rock particles. So there's another avenue for rock magnetism to look at a highly absorbent, radiative forcing component in dust. And you pointed out all these issues, and I think that was really valuable. You've given valuable lessons. Thank you.
Thank you. Well, we have about 700 samples from all over Australia, Australian dust source areas, and we just need to convince somebody to give us the funding to analyze them, but that's the plan. Yeah.
Awesome. Thanks again, Dave.
Okay.
Like I said, there are a couple of outstanding questions. We'll revisit some of
Yep.
these hopefully at 11:45.
So